So you have Vs, you have L. So you can remember we have the Vs, R, and L, and we have learned that the current is equal to uh, Vs over R minus Vs over R e to the negative t over L over R, or L over R, right? If I'm not mistaken, R over L. I think that's L over R, no? Okay. So that's the expression when you have the circuit plus minus like that, no? So, okay, assumption is that your current at 0 is equal to 0 amps. Okay, so that's how we understand. So meaning your inductor is uncharged. Now, if you look at the literature of inductor, it's actually a energy storage, no? Ang inductor, it can store energy for a brief moment. Or now, what if the circuit has an initial charge? What if I of 0 is not 0? Okay, what will be the expression of the circuit? Okay. Okay, so let's try to make a general. Actually, this one is not yet general. Okay, can actually make a more general case. So here in this switch, okay, so um, later on I will explain the switch. Know what will happen if you switch to A, okay, or switch to B. Okay, so now let's try to do if you can recall our expression, no, of this one. You have Bs, you have the R, and then you have the inductor. So you have Br plus Vl is equal to Vs, where Vs is a constant, and then you have Vr, you have I, which is common to all of them, I of t. So you have I of t times R plus Vl, which is L di of t over dt. Is equal to Vs, which is constant. Okay, and then you can arrange the expression. So you have di of t over dt, and then divide all the elements with L. So you will have Vs minus R I of t divided by L. Then cross multiply the term in the in the right will be in the denominator, while dt will be in the denominator of di over on the left side, no? So this becomes di of t over Vs minus R I of t over L is equal to d. Okay, so we have this expression here, and you can transfer the L in the numerator. Okay, now for the integration, we let u is equal to Vs Vs minus R I of t. Therefore, du, sorry, that implies, no? This implies du is equal to negative R di of t. Okay, so actually you can remove the R. Actually, anyway, we can continue, no? We can continue. Actually here we can remove the R. Sorry for that. It would be better if we remove the R inside, just like our original situation. So we have here L over R. You can put the R outside, and you have Vs over R minus I of t. Okay, and yep, so let u is equal to Vs over R minus I of t, then du, this implies that du is equal to negative di of t. Okay. The previous one, you can also do that, but I'd like to make this a bit simpler for you. So you have LR and then du over u. Okay, is equal to dt. And then, okay, we've learned that note or recall integral of du over u is equal to ln x plus the constant c. But here we know that we have this is a definite integration, so you have L over R integral of u of 0 and then u of t, then you have du over u is equal to from 0 to time. Okay, now why is it 0 to t? Because of course time is relative, you can start anytime, no? When you start, okay, I want to start today, so what is the initial value? So the initial value is this. What if at time 3 seconds later, what will be the value of my system? So then that would be the expression of this one. Okay, people are still okay. Then okay, so you have L over R. Sorry, if I should it should be negative from the expression below here. It should be negative, and so therefore this is negative LR ln of um, sorry, that should be ln of u of t minus ln of u of 0 is equal to t minus 0. Okay, so this is definite integral, so you don't write a constant because okay, you have a boundary. Then the subtraction of natural logarithm, you can make a division, okay, and then u of t, you can replace it already with bs over r minus I of t, and then you have bs over r minus the initial value of your current. Okay, so at time is equal to 0. So later on, you will learn that the initial conditions, no, is very important for solving integration and a system, no. So we can call it at time is equal to 0, I0. Okay, where I of 0 is equal to I. Not only 0, okay? Okay, so not only 0, but any value. Maybe our inductor is initially charged, di ba? Okay, and then you can transpose the negative LR, it becomes negative okay, T over L over R. Okay, cross multiply. Then exponentiate, then you will have Vs over R minus I of t, then divided by Vs over R minus I of 0 is equal to negative e to the negative t over uh, t over L over R. Okay, now you arrange the equation because our goal is to get the current so that you can solve the voltage across the resistor, the voltage across the inductor. Okay, you can do that. So therefore, arranging, we have I of okay, so I can even do that. Vs over R I of t is equal to Vs over R minus I of 0 is equal e to the negative t over L over R. Okay, then arranging that one, you will have I of t is equal to Vs over R minus Vs over R minus I of 0 e to the negative t over L over R. Okay, so actually this is the what we're looking for. Okay, if you have any questions, just let me know. Okay, so this is our expression. Now, how to look at this expression? What's the difference between this expression here with the expression Okay, what is the difference of this one here with the expression in this expression here? Can you see, can you spot the difference? Okay, you might wonder,
Minus IO, sir.
sorry, I,
Minus IO. I0, sir.
so I0 becomes, the I of 0 here, there's no I of 0 here because, why I of 0 is not found in the first equation?
Since it's assumed man na it's a value of 0, sir.
Okay, very good. Okay, if you look at this expression, this is the initial value here is 0. Okay, meaning we assume that initially the inductor is uncharged. Okay, meaning you can put the value I of 0 as the current. Okay, because this is a series, meaning you can assume that, okay, initially my IL of 0, which is the same as the I of 0, is equal to, let's say, 3 amps. Okay, so meaning you just replace this one with 3 amps. Okay, or you can repeat the whole process. You can repeat the whole process. Okay,